Welcome to the chemistry studio. Today's topic is molecularity. The number of reactant particles that take part in a chemical reaction that must collide simultaneously to bring about a chemical change is called molecularity. Molecularity, it is a theoretical concept. It can never be zero. It can never be zero. It is not considered more than 3 because probability of collision is very low. It cannot be negative and fractional. Example, unimolecular reaction. It decomposes to form nitrogen and 2 molecules of H2O. There is only one molecule, therefore it is unimolecular reaction. Bimolecular reaction. Like 2HI, 2 molecules of HI, they form H2 and I2. It is bimolecular. Trimolecular reaction. 2NO plus O2 forms 2NO2. Now next is pseudo first order reaction. The reaction which appears to be of second order but has first order. Example, hydrolysis of ester. This is methyl acetate. On hydrolysis, it forms acid and alcohol. While writing the rate of the reaction, we include concentration of ester, but we do not include the concentration of water, because water is taken in excess and there is negligible change in its concentration. Therefore, concentration of H2O cannot define rate, and therefore order comes out to be 1. Such reactions are pseudo first order reactions. Concentration of H2O is not included in rate law expression because H2O is taken in excess. Therefore, there is negligible change in its concentration. Now next topic is reaction mechanism. The slowest step of the reaction is the rate deciding step. Example, like NO2 plus CO, it forms NO plus CO2, and the rate of the reaction is R is equal to K NO2 power 2. We have to write the mechanism of this reaction. First step, we know that rate law is written from the slowest step. It means in slowest step there are two NO2 molecules which are reacting together. They react together to form the product. Out of these two, they will form NO. We know that. The rest is NO3. This is the slowest step. Now NO3 is not present in the overall reaction. Therefore, this NO3 has to be consumed. Now this NO3 will react with NO2 has already been used. This NO3 will react with CO. They will react together to form CO2 plus NO2. This is fast. So this is mechanism of this reaction. Let us take another example. Suppose H2O2, two molecules, they are reacting with I minus in the presence of I minus to form H2O and O2. Rate law given है R is equal to K H2O2 I माइनस, ये रेट लॉ गिवन है आपको. तो पहला स्टेप जो है from rate law, we know that rate law is written from the slowest step. It means H2O2 is reacting with I minus. अगर ये दोनों रिएक्ट करेंगे तो इन दोनों में से क्या बनेगा? We know that H2O तो कंफर्म बन रहा है. H2O बन गया, रेस्ट we are left with O and I. एक साथ लिख देंगे IO चार्ज माइनस. स्लो स्टेप. अगेन IO माइनस ओवरऑल रिएक्शन में नहीं है, हैज टू बी कंज्यूम्ड. अब फर्दर एक H2O2 यूज हो चुका है, हम एक और H2O2 यूज करेंगे. दोनों रिएक्ट करेंगे, इसमें से क्या बनेगा? एक H2 ऑलरेडी बन चुका है, एक H2O और बनेगा, प्लस और क्या बन सकता है? O2. और क्या बचा हमारे पास, I माइनस। ये स्टेप फास्ट हो गया। तो अगेन इसका मैकेनिज्म हमने ऐसे लिखा। एक और एग्जांपल ले लेते हैं। हमारे पास है 2NO प्लस O2 गिव्स 2NO2। इस बार आपको मैकेनिज्म गिवन है। NO प्लस O2 फॉर्म्स NO3। ये स्टेप फास्ट है। NO प्लस NO3 gives 2NO2। ये स्टेप स्लो है। स्लो स्टेप से हम रेट लिखते हैं हमेशा, R इज इक्वल टू K NO3। दिस इज द रेट लॉ फॉर दिस रिएक्शन, बट इस रेट लॉ में NO3 इंक्लूडेड है और NO3 ओवरऑल रिएक्शन में नहीं है। It means we have to replace the concentration of NO3. Let this K be K1. From the fast equation, we know that this reaction is in equilibrium. Therefore, equilibrium constant K2 will be product concentration upon reactant concentration. Product concentration upon reactant concentration. तो यहाँ से हम NO3 की वैल्यू निकाल लेंगे। NO3 concentration, NO3 is equal to K2 NOO2. Putting the value of NO3 over here, we get R is equal to K1 K2 NOO2 and concentration of NO. This K1 K2 को हम लिख देंगे ओवरऑल K, NO square and O2. This is rate law of this reaction. Now next topic is effect of catalyst. Effect of catalyst. Catalyst increase, or you can say alter, the rate of the reaction. But they themselves do not undergo any change, any chemical change. Catalyst form an intermediate with reactant which soon converts into product. Catalyst lowers down the required amount of activation energy. They do not affect the value of Gibbs energy and rate constant. The substances which decrease the rate are called inhibitors. Are called inhibitors. Example: KClO3 is converted into KCl plus O2 in the presence of MnO2. MnO2 is a catalyst which increases rate of the reaction. Now the next topic is collision theory. Collision theory. This theory considers that the product is formed as a result of collision among reactant particles. The number of collisions per unit volume per second is called collision frequency. Denoted by Z. Now we know that the rate also depends upon the number of particles having energy equal to activation energy or either greater than activation energy. The rate depends upon the fraction of molecules having energy equal to or greater than activation energy. That is rate. It depends upon the total number of particles colliding together and the particles having energy equal to or greater than activation energy. This Z is collision frequency and this is the fraction of molecules exponential raised to the power EA upon RT. This is fraction of the particles having energy equal to or greater than activation energy. Fraction of molecules having energy equal to or greater than. Now we know that rate not only depends upon the number of collision but on effective collision. Number of effective collision. Let P is the probability of effective collision. Effective collision. Therefore, rate will be equal to Z into P exponential EA upon RT. Z is the total number of collisions taking place. Out of those total number of collisions, how many collisions are effective collision? and the molecules having energy equal to or greater than activation energy will bring about the formation of product only. So it means rate depends upon probability of effective collision and activation energy. Activation energy. If we plot a graph of the fraction of molecules, these are fraction of molecules with kinetic energy. This is the graph at T degree Celsius. Suppose the molecule with high kinetic energy, the fraction is very low. If we increase the temperature, suppose by 10 degrees Celsius, this fraction of molecules having high kinetic energy will increase. It will increase. This is the fraction of the molecule which has increased. Suppose this graph has been plotted at T plus 10 degrees Celsius. Fraction of molecules, fraction of molecules having high kinetic energy. This graph is called Maxwell-Boltzmann curve. The total area of the curve remains same. That is all for today. Thank you.